Section 4.1.6. Angles of departure and arrival. How do you do this? You use the angle criterion, draw close to the singularity. Alright, what does it mean? That's all you have. This is all the amount of information. Okay? Section 4.1. So how do you do this? Obviously, we are saying that you choose one point. Okay? One point close to one singularity. So you can choose point here. That's supposed to be very close. Or you can choose something that is here. Alright? And then, okay, find out angles from all singularities to this particular 12 point. Okay? And then we use our angle criterion. Alright? So, I think it might sound a bit complex to you. Let's just go through this. Okay, first of all, look at the point. Angle of departure. As I said, choose a 12 point. Okay, so here you can use the same point here, minus 4 plus j. Okay, so if this is your 12 point, alright, what you need to mention now is angles from the 0 to this 12 point, from this pole to this 12 point, from this pole to this 12 point. Okay, and the angle that this 12 point is going to move away. Alright, so if we look at this, okay, what we're saying is you find out what is this angle. Okay, and this angle is beta 3. This angle beta 2. Okay, this angle beta 1. Okay, so this is the meaning of angle, right? To the 12 point. Okay, so obviously, this is 2. This is 1. Alright? So you can find an angle here. Okay, and this angle is tangent inverse 1/2, right? This angle. Is tangent inverse 1/2, right? Right. Not sure. Opposite is 1. Adjacent is 2. Minus 1 to minus 4, 2. Okay? So this angle is tangent inverse 1/2. I want theta 3. So can I understand that theta 3 is 180 degrees minus tangent inverse 1/2? Okay? But when you punch into your calculator, this is a very silly mistake that most students will make. Make sure your calculator is in degrees. Okay, let's change that to degrees before you do the subtraction. Okay? Make sure now it's 153.4. Alright? Okay? Theta 2, how much is it? How much is theta 2? How much is theta 2? 90. How much is theta 1? How much is it? 90.
That's all done.
So once you note down the angles for theta 1, 2, 3, angle of departure, theta, for this particular point, minus 4 plus j, can be found by angle criterion, summation of angles extended from 0, which is theta 3, minus angles extended from poles, will be minus 180. Alright? So this is what you should do. The angles extended from 0 is theta 3 minus, in bracket, theta 1 plus theta 2 plus theta. Okay? It's minus 180. And what you want to find is theta for that particular point, minus 4 plus j. And you find that theta is 153.43. Okay? And this is your angle of departure. Most of you have a tendency to just copy down things right beside your notes, whereby there's only very little space. Okay, and once you copy, you come back, you revise, you cannot really read what you have copied. Okay, so if you can, do the exercise on a proper piece of paper, or your Root-Locus on a proper piece of graph paper, obviously. Okay, so things will be easier when you copy revision. Alright? So far so good, right? Okay? So now you have the angle of departure. Can you just complete your Root-Locus? Okay? So what we are saying now is now is the time for you to use your compass. Digital compass protractor. Okay. So any questions on this? First, any question on this thing? Any questions on angle of departure? Okay, so let me just repeat for the benefit of those who are not able to follow. Okay, how do we find angle of departure or angle of arrival? Alright? Choose a trial point. Okay, so here we choose a trial point at minus 4 plus j. If you say that this is your trial point, okay, find the angles subtended from all the other singularities with the trial point. Okay? So there's a 0 here. What's the angle from this 0 to the trial point? Is theta 3. There's a pole here. What's the angle from this pole to the trial point? Is theta 2. There's another pole here. Angle from this pole to the trial point is theta 1. What about this trial point itself? Okay? Alright, the angle will be the angle of departure. Alright, which will be theta. Okay? So if you got the graphical idea, calculate theta 3, theta 2, and theta 1. Write them down. This is the angle criterion. Okay, so you have angles subtended from 0, which is theta 3, minus, in bracket, all the angles subtended from the poles, which is theta 1, theta 2, plus theta for the trial point. Equals to 180, minus 180. Okay? And this theta for the trial point is what you want to find. Because it tells you how your pole at minus 4 plus j is going to move away. Okay? To this supposedly trial point. Alright? So if you choose a trial point very near to minus 4 plus j, this theta will tell you how your pole at minus 4 plus j will move towards the trial point. Okay? So you might also want to say, man, can I use minus 4.1 plus j? Yeah, sure. Can I use minus 4 plus 1.1j. Yeah? Can. Okay? Alright, but for simplicity, I just choose minus 4 plus j. Something near to minus 4 plus j. Alright? And this last bit, this angle, will tell me how my minus 4 plus j is going to move towards this troughole. Okay, and this will tell me how I'm going to leave minus 4 plus j. What's the angle of departure? Alright? So now you've got all this information. Draw your Root-Locus. Okay? So if you ignore this for the time being. Alright? What you need to draw, you must have the imaginary axis, your real axis, the 0 and minus 2, the 4 and minus 4, another 4 and minus 4 plus j, another 4 and minus 4 minus j. Okay? Your asymptote center, minus 5, asymptote angles, plus 90 minus 90, is your asymptote. You tell me that this part of the real axis is on the locus, and this pole will move towards the 0 in this way. Show me the arrow. Okay? You calculate what is theta 3, theta 1, and theta 2. Okay? And you calculate theta, which is how my pole is going to move to my pole point, which is very near to my pole. It's 103.43. Okay, so if you put your protractor here on the point, okay, and you measure 153.43, okay, and you mark that with a line, okay, you say that this is 153.43 degrees, okay, draw something along this line and then branch and then move towards your center. Okay, but you do not touch your asymptote because asymptote is something that moves towards the right? If this complex pole will move in this manner, the same will happen to the other complex pole in opposite direction, right? Okay? Alright, so this will give you 12 marks, including the calculation of angle of departure. So if you do not calculate angle of departure, but you just think that, hey, I think that these 2 points are going to move maybe in this way, and you just draw it, you do not get the 2 marks, right? Because you did not calculate angle of departure, right? And our minus marks for not including the imaginary and real axis as well. Okay? So this is the Root-Locus. Alright? That's straightforward. Okay, so things will get easier and easier as you move along, right? Part 2, from your diagram, find the value of K that will give the complex closed-loop poles a damping factor of 0.8. And that's 4 marks. Okay, so you know, okay, the Root-Locus is a plot of the closed-loop poles. Okay, where K equals to 0 to K equals to infinity. So when K equals to 0, the closed-loop poles will start at open-loop poles, right? This 3 position. Yes? When K tends to infinity, this closed-loop pole at this position will end at open-loop 0. Right? So this is the closed-loop pole when K is 0. This is the closed-loop pole when K is infinite. These two, this is the closed-loop pole location when K is 0. And he moved towards the asymptote. And the further it travels, the more infinite K is, right? And the other way around. So I'm going to ask you what is the value of K that will give me my system, okay, or my closed-loop poles, a damping factor of 0.8. So if we look at the introduction, we tell you angle, cosine of this angle, cosine of theta here, is your damping factor 0.8. Okay? Alright? Okay? So the damping factor 0.8 is cosine theta. And theta is 36.87 degrees. Alright, next thing you do, you mark 36.87 on the graph with a protractor. For those who are taking photos, please make sure when you get back home or later, write it down with pen and paper, because I take photos, I take and then I forget what I do, right? So do that, okay? Alright, if you don't have a protractor, it's not the end of the world. Okay, you can still use this thing, this adjacent and hypotenuse thing, equal to 0.8. And then based on the scale that you have drawn your graph with, if you draw 2 cm to 1 unit, okay, you can also use your ruler to measure that the hypotenuse is 12.5 cm. You can still find that angle, right? Okay? So you know this is 36.87 degrees. With a protractor. If you have a protractor, you don't need the alternative method, right? So I believe every one of you should bring a protractor, if you understand. Okay? Alright, put your protractor there. See that it is 36.8. Okay? Can you read this? Alright? 36.8 degrees. So you draw a line along 36.8 degrees of the origin. So make sure you place your protractor right in the middle. Don't place your protractor here and mark 36.8 and then draw me something else. Okay, if you place your protractor right in the middle here, you measure 36.8, you mark this point, you draw a line connecting this point and the origin. Okay? Alright? And then see how the point intersects your Root-Locus. Okay, so this is the point. Okay, they'll give you a damping factor of 0.8. Alright? After you know that this is the point, how do you find A? How do you find the value of A? What you have at this stage? Okay, let me just what you have at this stage is not the value of A, right? What you have at this stage is just the point of intersection. Okay? So if you have this point of intersection, the value of S, which you can read from the graph, how do you find the value of K? What equation do you use? Huh? K, integration, equation, right? Okay? Basically, what you need to do next, okay, whereby you need a ruler, okay, is to find out the distances from this point of intersection to your poles. So you've got one pole here, right? Okay? Can you read this distance to this pole? the distance to the next pole. It's 1.5. Right? The distance from here, the point of intersection, to your pole. Okay? And then you have another pole. Here, move your ruler. It's 9.5. Okay? And after that, so you have got all the distances to open loop poles, right? To put into your gain calibration equation. Yes? Okay? What else do you need? This is your gain calibration. Now that you've got the distances to open loop poles, what else do you need? Distances to open loop, zeros. Okay? So next thing you do, position your ruler at the 0. And you measure. It's about 9.5. Okay? Then again, you have to take note of the scale. Alright? So here, okay, you do this, put in the gain calibration equation. So K is the product of all distances to open the poles over the product of all distances to open the zeros. So we measured 5.7, 7.5 and 9.5. But divide that over the scale. If you have drawn your graph as 2 cm to 1 unit, you divide by 2. If you have drawn your graph as 1 cm to 1 unit, you divide by 1. Okay? Anybody who doesn't know how to draw a scale? I have a show of hands if you are not sure how to read the scale. So everybody knows how to read the scale. Yeah? Okay? Alright? So what was I saying? I was saying this. If you had drawn your locus like this, okay, this is 2 cm to 1 unit. Okay? You divide your length by 2 because you need the units and not the cm. Alright? Okay? So if you look at here, okay, this is also 2 cm. So when you draw a Root-Locus, okay, make sure you keep your scale consistent for both the real axis and the imaginary axis. Alright? Okay? So this is how it ended up with 10.67. Alright, and this is 4 marks. This is 4 marks. Okay? Okay, the last part of the question.
Scale 0 to 1 unit. Oh, 1 unit. 0 to 1 unit. 0 to 1 unit. 那个 0 to 1 unit. 对，什么意思？是要 times 2
Let me just go through the last part of the question very quickly. I'll leave this here. Okay? The last part of the question says, comment on the overshoot you expect to see the step response of this system. Okay? So if you have a step response, what do you think is the overshoot that you tend to expect to see? Alright? Okay, so from the introduction, we tell you that overshoot is e to the power minus pi tangent theta. Okay, so at the point where my damping factor is 0.8, cosine theta is 0.8, tangent theta is 4.3. Okay, what is cotangent? Theta is just 1 over tangent theta. From this, you know the overshoot is about this 1.5%. We say that that's relatively low. Okay? You can do all of this, you get 20 marks.
Sure. 我回家对比这个样。我等一下拿灯就走。
Alright? And then many students will have a question. So the map, I think that's something that I didn't actually consider when I was doing this question because, let me just flash that question. There's a hint here that I did not use. Okay? The hint is there, it's always there, just to help students if they need to solve for anything like that. But you don't have that, so you don't have to use it. Okay? So we do not give you an option of whether you want to use the hint or not. Things are always there. Anything, you know, you think that something exists, you use the hint. If you think that something doesn't exist, then it's not. Alright? Okay, we will leave for I think 10 minutes break. We'll come back at 12:25. Meanwhile, if you have any questions at all about this particular example, please come down and explain.